Welcome students to the MOOCs lecture series on statistical inference. In the last lecture, we have talked about point estimation of the parameters of the underlying distribution from which a sample x 1, x 2, x n is taken. In particular, we have discussed two methods. Method of moments and method of maximum likelihood. In method of moments, what we have done? We have calculated sample raw moments from the sample x 1, x 2, x n, and we have equated that with the theoretical moments as given by the distribution under consideration. And by equating them, we have formed equations and we obtained the estimate for different parameters by solving those equations. On the other hand, the philosophy of maximum likelihood is slightly different. Here, we try to differentiate the likelihood function of x 1, x 2, x n under the parameter theta by taking its derivative or partial derivative with respect to theta and equating it to 0. So that by solving for theta, we get a function of x 1, x 2, x n which maximizes the likelihood function, or in other words which maximizes the probability of obtaining the sample x 1, x 2, x n, and the theta for which that is maximized is considered to be the maximum likelihood estimated. However, the problem of point estimation is that it is on the basis of sample x 1, x 2, x n, and based on that we are trying to estimate the value of the parameter theta. As I have already shown you an example, suppose a coin is tossed n times and the outcomes are say 1 0 0 1 0 0 0 1 0 0. That is, there are 3 heads and remaining tails. Based on that, if we try to estimate p, then p hat comes out to be say 0.3. But suppose we make another experiment of the same coin, there may be 4 heads or there may be 5 heads, and accordingly the p hat will change according to the number of samples. Hence, it is prudent to obtain an interval of the form say a b such that probability theta belongs to A B is very high, say 95% or 99%. What is the advantage? The advantage that we are very confident that based on the sample we can see that theta is going to belong to this interval with a very high probability. That assurance we cannot give with respect to point estimation. Hence comes the idea of interval estimation. So, what we do here? We want to obtain statistics T1 and T2 based on the sample x1, x2, xn such that probability theta less than equal to T1 is equal to say alpha 1 and probability theta greater than equal to T2 is equal to alpha 2. So, pictorially suppose this is the range of theta, which we have already denoted as capital theta. Depending upon the distribution and the parameter, the theta will change, but suppose we have T1 here such that probability theta belongs to this interval or theta less than equal to T1 is equal to alpha 1, and suppose this is the T2 such that probability theta greater than equal to T2 is alpha 2. Then probability T1 less than equal to theta less than equal to T2, or say let them be strict inequality, it does not matter because it is a continuous case, and this probability is therefore going to be 1 minus alpha 1 minus alpha 2. If alpha 1 plus alpha 2 is equal to alpha, then this interval has a probability say 1 minus alpha that theta will lie in this interval. Question is, how to obtain this interval? And the confidence of these intervals. By confidence we mean the probability that the parameter will remain within that interval T 1 and T 2. Typically, we consider 95% and 99% confidence intervals. Consider 95%. Suppose this is the range of theta. We want T 2 such that in this there is 2.5% chance that the variable will occur on this side of T 2 and say T 1 such that on this side also there is 2.5% chance that the theta will occur in this region. So, the 95% confidence interval for theta is this. If it is 99%, then we will look at a T 2 such that the occurrence here is only 0.5% and the occurrence probability of here is 0.5%. Therefore, that theta will occur in this interval has the chance 99%. So, these are the confidence intervals that we try to obtain for the parameter theta or with the help of the sample x 1, x 2, x n. To obtain these limits, we have different tables. For this class, I shall show the normal table and chi-square table. So, let us first understand how to see the normal table. We know the shape of the normal curve is somewhat like this. Consider this is 0. Let us just look at normal 0 1, because for any other normal with mu and sigma square, we can convert it to the standard normal distribution. We know that probability z, which is standard normal, less than equal to 0 is equal to 0.5. So, for 95%, we will look at the value, say call it z 0.975, because the area below this is equal to 97.5%. that is this area is 2.5%, and since Z is symmetric, this value such that below this is 2.5% is going to be minus of this. Therefore, Z of 0.025 is equal to minus of Z of 0.975. So, there are tables where these values are tabulated. First, let me show you the normal table. So, if you look at the table, it is showing standard normal distribution table values represent area to the left of the Z score, as you can see that. So, in this table there are all the values tabulated. Let us see the value corresponding to 0.975. Consider this value. This is 0.975. So, we have to obtain the x value or the value on the real line such that probability of standard normal variate less than equal to this is 0.975. How to obtain this? We first look at the left side of this table and we can see the value given is 1.96, 1.9 as you can see. So, that is 1.9, and for the second decimal place we go above and we can find 6. Therefore, we get 1.96. In a similar way, suppose we want 99% confidence interval. Therefore, what we will be looking at? We will be looking at a value such that below that the probability of occurrence is going to be 0.995. So, again we look at the table and we find that this is the value which is 0.99492, and if we go further we get 0.99506. Therefore, 0.995 we would expect is somewhere at the middle. Now, if I go along the row very slowly, we can see that the value corresponding to this is 2.5. As I am dragging my pen slowly, you can see that the values are coming out to be 0.99492 and 0.99506. So, if we go above, we can find the values are here along this column are 0.7 and 0.8. So, we can say 2.58 is the value such that a standard normal distribution will have a value less than 2.58, has the chance 0.995 or has the probability 0.995, or it is 99.5% chance that the standard normal value will obtain will have a value below, or a standard normal variate will have a value below 2.58. Therefore, we need to remember at least these two values. So, you remember this table. For standard normal, I write it both sided. For 1%, the value is 2.58, as we have just observed. Above 2.58, the chance is only 0.5%, and below minus 2.58, the chance is only 0.5%. So, together we have 1%, or the 99% confidence interval is minus 2.58 to 2.58. Similarly, when we are looking at say 5% here, then this value we have just seen is 1.96, or 95% confidence interval is minus 1.96 to 1.96. So, these two values you need to remember, because typically these are the values that we use. Of course, there are many other values, as you have seen in the table, it is full with values. So, for normal, for different level of confidence, we can actually obtain the value from the table, but for this class we restrict ourselves only to the two cases, both sided interval and 95% confidence and 99% confidence. How to use this table? So, consider this following problem. Suppose a coin is tossed (4,000) times and number of heads obtained is 2400. Question is, can we consider the coin to be unbiased? And second question, what will be the interval between which the number of heads should lie so that we can consider the coin to be unbiased with 95% confidence. So, let me explain the problem again. So, there is a coin, we tossed it 4,000 times. If it is unbiased, expected number of heads is equal to 2000 and expected number of tail is also 2000. But it does not actually mean that in the result we will get exactly 2000 heads and exactly 2000 tails. That will not happen in general. So, the what we want to estimate it that what is the value of p or the probability of success or the probability of getting a head in a toss given this result. Okay. So, we solve it in the following way. Since the number of trials is high, that is 4,000 is a large number, we can consider normal approximation. To the proportion of heads obtained. Let p be the random variable denoting the proportion of heads. Therefore, expected value of p is equal to half and variance of p as we know is equal to p q by n is equal to half into half divided by 4,000. Therefore, p minus half upon root over half into half upon 4,000 may be considered as normal 0 1. Since we obtained 2400 number of heads, therefore, obtained proportion is equal to 2400 divided by 4,000 is equal to 6 upon 10 is equal to 3 upon 5. Therefore, 3 upon 5 minus half divided by root over half into 4000 can be assumed to be normal 0 1. Now, this denominator is half into root over 1 upon 4000 is equal to half into 1 by 20 into 1 upon root 10 is equal to 1 upon 40 into 1 upon root 10. Therefore, the obtained value of the normal 0 1 variable is 3 by 5 minus half upon 1 by 40 into 1 by root 10 is equal to 6 minus 5 upon 10 divided by 1 upon 40 into 1 upon root 10 is equal to 1 upon 10 into 40 into root 10, which is equal to 4 into root 10 and which is much greater than 3. Typically, almost 100% observation of normal 0 1 variable lies in the interval -3 to +3. Since the obtained value is much greater than 3, we can say the coin is not unbiased. If the coin were unbiased, then it is the value obtained should lie in the interval -3 to +3. The second part of the question says that what should be the number of heads, or part B is what should be the number of heads to consider the coin to be unbiased with 95% confidence. We know number of heads is follow binomial in P. So, here n is equal to 4000, P is equal to half. Therefore, expected number of heads is equal to n by 2 is equal to 2000, and variance is equal to NPQ is equal to 4000 into half is equal to 1000. Therefore, n minus 2000 divided by root over 1000 has to be less than equal to 1.96. This we have already obtained, as we are looking for 95% confidence, or in other words, if n is the number of heads, then modulus of n minus 2000 divided by 10 root 10 has to be less than equal to 1.96, or modulus of n minus 2000 is less than equal to 1.96 into 10 root 10, or 2000 minus 1.96 into 10 root 10 has to be less than equal to n less than equal to 2000 plus 1.96 into 10 root 10. Now, 1.96 into 10 root 10 is approximately 62. Therefore, the 95% confidence interval for number of heads to consider the coin to be unbiased is 2000 minus 62 to 2000 plus 62 is equal to 1938, 2062. Or in other words, if we toss the coin 4000 times and the number of heads is obtained in this range between these two values, then we are 95% confident that this coin is unbiased. Let us look at another problem. Consider normal mu sigma square, and we want to find confidence interval for sigma square. Let us consider the case that mu is known. In that case, sigma xi minus mu whole square I is equal to 1 to n divided by sigma square. We know that it is a chi-square with n degrees of freedom, where x1, x2, xn is the sample obtained. In general, the chi-square distribution will have a shape like this. So, it is different from normal 0 1, as chi-square is in 0 to infinity. It is a positive random variable, therefore, it ranges over 0 to infinity, and secondly, it is not symmetric around mean. Also, the shape of the chi-square changes with the degrees of freedom. As degrees of freedom increases, a chi-square may take a shape like this. Therefore, for different degrees of freedom, we need to obtain the cutoff values for getting the desired interval. Therefore, we will be looking at a value here such that this probability is alpha by 2. We will be looking at a value here such that this probability is also alpha by 2. So, that this is the 100 minus alpha % confidence interval for chi-square. So, let me show the chi-square table. So, if you look at, you can see that it is a chi-square distribution table. The values are tabulated for different degrees of freedom, and the values are given for this point such that the shaded area is equal to alpha. That means, the probability the chi-square distribution is greater than this value, that probability is alpha, and therefore, when we are looking at a 95% confidence interval, we look at this value such that the above this the probability is only 2.5%. Also, we will look at a value here such that above that the probability is 97.5%, or in decimal form this value will give corresponding to chi-square with 0.975, and for this we are looking at the value for chi-square with 0.025. How do we get the values? If we look at the table, we will find that the values are given for different degrees of freedom 1, 2, 3, 4, and here you can see the values tabulated are for 0.975, and if I go further to the right, we can see the values are tabulated for 0.025. In fact, it is given for 0.005, 0.010, like that. For a fixed set of alpha, the values have been computed. In particular, let us look at chi-square with 100 degrees of freedom. Look at the value, it is 100 degrees of freedom, and corresponding to 0.975, this value is 74.22. That means, a chi-square 100 degrees of freedom will take a value greater than equal to 74.222 with probability 9.975, or in 97.5 cases out of 100. And if we go further, we can see that for 0 to 5, the values are 129.561. Okay. So, let us consider one problem. Suppose x 1, x 2, x 100 is a sample from normal 1 comma sigma square, such that sigma x I minus 1 whole square is equal to 200. Find 95% confidence interval for sigma square. Since x 1, x 2, x 100 are from normal with 1 comma sigma square, therefore, sigma x I minus 1 whole square upon sigma square is chi-square with 100 degrees of freedom. We have just seen the 95% confidence interval is 74.22 to 129.56. Therefore, probability 74.22 less than equal to sigma x I minus 1 whole square upon sigma square less than equal to 129.56 is equal to 95%. or probability 1 upon 129.56 less than equal to sigma square upon sigma xi minus 1 whole square less than equal to 1 upon 74.22 is equal to 95%, or probability sigma xi minus 1 whole square upon 129.56 less than equal to sigma square less than equal to sigma xi minus 1 whole square upon 74.22 is equal to 95%. Since this is given to be 200, or probability 200 upon 129.56 less than equal to sigma square less than equal to 200 upon 74.22 is equal to 95%, or probability 1.54 less than equal to sigma square less than equal to 2.69 is equal to 95%. Therefore, 95% confidence interval for sigma square is equal to 1.54 comma 2.69. So, the problems that we solved, they are all both sided we have taken. If we want to take one sided interval, say consider normal 0 1 and we want one sided interval, that is if z follows normal 0 1, we are looking at z alpha such that probability z less than equal to z alpha is equal to say 95%, then it is one sided interval, or in other words, if it is a normal curve, we are looking at z alpha such that this area is 95%, that is this area is 5%. These are called one sided intervals, and for normal 0 1 at 95%, this value is 1.64. If we are looking at 99% confidence interval, and both sided, therefore, we are looking at this is only 0.5% and this is 0.5%. That means only 1% are beyond this range, therefore, this is 99%. Then for standard normal, this value is 2.58. You should remember these values for solving problems with respect to interval estimation. Okay, students, with that I conclude my lectures on theory of estimation. We have learned the properties of estimators, we have learned how to estimate the value of a parameter from a sample when we are looking at point estimation. Also today we have seen how to look at an interval estimation for a parameter given a sample x 1, x 2, x n. In the next class, I shall start the last chapter of statistical inference, namely testing of hypothesis. Thank you.